EE-371 Electromagnetic Fields Theory, lecture number 25. The topic of this lecture is potential gradient. In today's lecture you will understand that what is potential gradient and how to use the potential gradient to convert the integral form of potential into differential form. In last lectures we have obtained these two relations, that is potential in term of electric field and potential in term of volume charge densities. In obtaining these two relations we have used the concept of work done in electromagnetics field theory, that is to bring a unit positive charge from one point, let's say from point B to point A in the field of another fixed charge. We have concluded that the work done doesn't depends on the path of integration, but the work done actually depends on the initial point and the final point, that is point A and point B, where we assume that the charge is at rest. Using the concept of work done electromagnetics, we have obtained these two relations. Now if you look at these two relations, so E field and the volume charge density, whether it is volume charge density, surface charge density or line charge densities, so these quantities are not can not easily measure in the laboratory. We need an expression that we can easily utilize in the laboratory to give us electric field and volume charge density. So in the laboratory we can easily use the potential, that is we can easily measure the voltage. Using voltage then we will be able to measure the electric field. So we have to convert this integral form of potential in terms of electric field to differential form. For this purpose we are going to use the concept of potential gradient. So let us see what is potential gradient, and before going into detailed discussion I would like to first define what is the gradient. So let us consider a room in which we have a heater. The heater produces temperature. Now what is mm, the potential, the gradient? So the gradient basically defined as the maximum variation in any scalar quantity in a specific direction. So that is known as potential gradient. For example, we follow this path, this route. Let's suppose this is our L1. So going along this path, we gradually feel the heating effect more and more as we go close to the heater. We can follow different paths. For example, let's say this one, along this one. So when we move along this path L2, so along this path we will feel more heating effect than L1. For example, along this path, let's say this is L3. So along L3 we will feel more and more heating effect as compared to L2 and L1. So this means that following this path we can feel maximum variation in the temperature. So this effect is known as the gradient. But if you look at this phenomenon, the temperature is directed in upward direction, and we are moving in downward direction. So the two things are opposite to each other. That is, the cause and effect are anti-parallel to each other. This actually produce a negative gradient and also produce a very important relation. So we will be using the gradient concept to achieve to convert this expression from integral form to differential form. To convert this expression from integral form to differential form, let us consider uh, a region that is occupied by the streamline. The streamline are originated from an unspecified source from left side and terminated on an unspecified source on right side. In between these sources, positive for instance and negative source on the left right side, uh, at each and every point the electric and potential are varying, going back and forth in between the two sources, two positive negative charge. The potential and electric field is varying, but we are actually going to see the potential variation at very small scale, that is for differential length. So let us consider a differential length delta L, which makes an angle theta with respect to E field or with respect to the potential. So for the incremental length delta L, we may write the integral form of potential relation in incremental form delta V equal to minus E dot delta L, or we can write this equation, this one, in this form, that is delta V divided by delta L is equal to minus E cosine theta. As we have defined that the gradient is basically the maximum variation on any scalar quantity in a specific direction. So looking to this relation, now we will decide that what should we do with this relation to get maximum variation in incremental potential with respect to the length. So this can be achieved using two possible conditions. Number one, delta V by delta L would maximum if either cosine theta get minus 1 or electric field and dV by dL are anti-parallel to each other. So in that case we will be able to get the maximum variation in potential with respect to L. In order to achieve the maximum variation in potential with respect to space, uh, either the cosine theta must get negative value, minus 1 value, or the electric field and the the variation in potential with respect to space length must be anti-parallel to each other. So let us consider space which is occupied by multiple equipotential surfaces. What is basically equipotential surface? A surface that has same potential, that is known as equipotential surface. So um, the potential difference between the two equipotential surface is 10 volt. Uh, on the left side we have highest equipotential surface. On the left side we have the minimum equipotential surface. Now we have and remember that electric field is directed from higher potential equipotential surface to lower equipotential surface. And let us consider that the normal to these surfaces are directed towards higher equipotential surface. Let's say A n unit vector. A n unit vector is directed to higher equipotential surfaces. For instance, we choose um, a path, for example, along I move along any equipotential surface. So in this case, we do no work because the potential along the equipotential surfaces are the same. Let us we are actually going to look to search path along which we get maximum variation. For example, I follow this path. So along this path, the variation in potential is a little bit larger, maximum, and the electric field is also in opposite direction to this variation. Now let us consider this path, and along this path we can get maximum variation in potential with respect to length delta L. For instance, this is L length. So along this path we can get maximum variation and potential with respect to space, and also the electric field is anti-parallel to this variation. So coming back to this relation, by keeping the direction of partial V by partial L and E anti-parallel to each other, we can get maximum variation and potential with respect to length. So this is known as the negative gradient of scalar potential, and the negative gradient of scalar potential in any specific direction give return us the electric field. In general, we can write the electric field in this form, replacing L by N represent the normal to the equipotential surfaces. So E equal to minus dV by dN. A n unit vector represent normal to the surface. Any vector that is perpendicular to tangent line is known as normal. Uh, this equation basically interprets the process of finding the electric field intensity from the potential function. This is in general, or you can write this the above equation in this form, that is dV by dN having maximum value, and then in this in an unit vector direction produce what electric field, return as electric field. You can also represent dV by dN an unit vector in a grade V minus grade V, or you can write this equation in this form, that is E field is equal to minus del V, where del V represent the Nebel operator. So the negative gradient of scalar potential produce a vector electric field, electrostatic field, and this actually produce a vector quantity. Now let us learn that how to write this journal expression in rectangular coordinate system and cylindrical coordinate system and spherical coordinate system. So let us suppose that the potential is a unique function of x, y, z in rectangular coordinate system. Then we can write the total differentiation of potential in this form. That is dv equal to partial v by partial x unit vector plus partial v by partial y ay unit vector plus partial v by partial z az unit vector. Let us assume this is our equation number I, and we also know that for instance electric field has three components along each axis. So from the differential relation of integral form of potential we can write dv equal to minus E dot dl. So using the differential length in rectangular coordinate system and the electric field we obtain this one. Now compare equation number 1 with equation number 2. So we obtained E sub x equal to minus partial v by partial x, Ey by equal to minus partial v by partial y, E sub z equal to minus partial v by partial z. Substituting these components of electric field into the expression of electric field, and eventually we come across this relation which represent the negative scalar potential of negative gradient of scalar potential, which actually gave us electric field, where delta represent the vector operator in rectangular coordinate system and is given by this relation. So the product of nebula operator or delta operator with potential function represent the negative gradient of scalar potential, which return us the electric field. Similarly, one can write the one can expand the negative gradient of scalar potential in cylindrical coordinate system and in spherical coordinate system using these two relations. This represent the gradient of scalar potential in cylindrical coordinate system, and this one represent the gradient of scalar potential in spherical coordinate system, and the above relation represent the gradient of scalar potential in rectangular coordinate system. So from this lecture we basically understand that how to convert the integral form of potential function which we actually determine in term of electric field to differential form. So in order to convert the integral form of potential relation in term of electric field to differential form, we use the concept of the gradient of scalar potential V. So gradient basically represent the maximum variation of potential in any specific direction. But remember that the gradient of scalar potential could only give us the electric field when the electric field and the variation in potential with respect to space are anti-parallel to each other. So that actually define the the gradient or the negative gradient of scalar potential, which return us the electric field. Let us try a drill problem. The drill problem D4.8. Problem is given on page 95. D4.8. We have given the potential in cylindrical coordinate system, and we have asked to find the potential at rho equal to 3 meter, phi equal to 60 degree, and z equal to 2 meter. This is the field point where we have asked to define the potential, the electric field, E, the magnitude of electric field, and dV by dN, an unit vector, a unit normal, the volume charge density in free space. So let us see the solution. So actually the potential in drill problem 4.8 is given in cylindrical coordinate system. We have also given the value of radial axis, phi axis, and z. Z is 2 meter. Uh, Plugging these values in this expression, and after some numerical manipulation, we get the potential at P point equal to 30 volt, which is exactly matched with the answer given in the book. Now let us how to obtain the electric field. Now we have asked to find the electric field. So basically the in order to find the electric field from the given potential, expand the negative gradient of scalar potential in cylindrical coordinate system, which is given by this relation. First differentiate the given potential with respect to rho, and then plug in the values of rho, z, and phi. So the variation of v with respect to rho at p point equal to 10, and then evaluate the second term, differentiate the given potential with respect to phi, and then plug in the values of rho, phi, and z, and we finally come across this value, that is minus 17.32. Then evaluate the partial v by partial z, or differentiate v with respect to z, and then plug in the value of rho, z, phi. The value of partial v by partial z become equal to minus 24. So plug in all these values, that is the partial v by partial rho, the numerical value of partial v by partial rho, numerical value of 1 upon rho partial v by partial phi, and the numerical value of partial v by partial z, which is minus 24. So the electric field at P point 36022 is equal to minus 10 a rho unit vectors plus 17.32 a phi unit vector, and blah blah. Now how to get the magnitude? So that is very easy, straightforward. Take the magnitude of this vector, so this become equal to 31.24. We have asked to define this the gradient, the scalar value of dV by dN. So we know this expression, that is E equal to minus dV by dN. An capital N represent the unit normal to any surface. So actually this thing dV by dN is equal to the scalar component of d, or the magnitude of E field, so which we have obtained in previous part part C, that is 31.24 volt per meter. Now again, how to obtain the unit normal? So that is very easy. Thus divide using this expression, E equal to minus dV by dN, and to n unit vector, and then divide this whole expression by dV by dN. We know the electric field, and we also know the magnitude of electric field, so just divide the electric field by its magnitude, so we could obtain the unit normal. uh, then how to obtain the value of volume charge density? So we know the um, potential function, differentiate the potential function, first define the gradient of scalar potential V, and using the expression for electric field, plug in the value of partial V by partial rho, 1 upon rho partial V by partial phi, partial V by partial Z, using the given potential function, and then use once you get electric field, then it is very easy to obtain the volume charge density. As D field, the electric flux density is equal to epsilon naught time E, and we also know that how to expand the divergence in cylindrical coordinate system. So using this relation and electric field expression, um, differentiate the electric field expression with respect to rho, with respect to phi, and with respect to z, and after some mathematical manipulation and using the numerical values, we obtain the value of rho v equal to minus 234 pc per picocoulomb per cubic meter, which is exactly matched with the answer given in the book.